Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this lesson we're going to look at Year 1 topics of collision theory and Boltzmann distribution. And so we're going to build on some GCSE knowledge of rates of reaction and then look at some new ideas with Boltzmann distribution graphs. So imagine we have our two reactants A and B, and we can also represent the energy of A and B, the reactants, on an energy profile. So we've got energy on the y-axis, and then on the x-axis we've got reaction coordinate, or progress of reaction. And so we're going to set our energy just arbitrarily here for A and B are reactants. Now if we imagine A and B as simple particles, almost like billiard balls or pool balls, and these particles have kinetic energy and randomly can move into any direction. So A could move this way, it could move this way, etc. However, if A and B both move towards each other, then they will undergo collision. So if this collision occurs, it has a possibility of actually producing something new, and that would be the products, just then shown in our equation like so. And let's imagine this is an exothermic reaction. So on the energy profile diagram, the energy of C and D are less than that of A and B. So relatively, A and B is up here and down here. So we've got an exothermic reaction in terms of its enthalpy change. Now in order for this transformation of A and B to occur into C and D, this collision of A and B needs to occur at a specific energy. And this minimum energy is known as the activation energy. This is also given the symbol EA. So then going back to our energy diagram, what we're saying is that A and B, the reactants, need this magnitude or size of energy, called the activation energy, in order to be converted to C and D. So we can think of this as an uphill to downhill journey. And so if A and B have enough energy on collision, then they will be transformed into C and D, which has a lower energy overall, because this is an exothermic reaction. Same principle applies if it was an endothermic reaction, just that the C and D energy level would be up here, but you'd still get the same uphill to downhill, but it wouldn't be as prominent if the energy level was here. So in terms of these particles colliding, there are a number of different conditions that you can change in a reaction in order to make these collisions more likely to occur or just more often to occur. And these are what we do as chemists in order to basically get a reaction to occur quicker. And we call that the overall effect is the rate of reaction increases. And in each of these scenarios, we're going to look at how to increase the rate of reaction, but by changing different types of conditions that we can change. So in all of these, you've got a cause that leads to an overall effect. And on the way there, we're going to have two little stop-offs in order to explain this. We're going to first of all comment on the particles, and then we're going to comment on how that effect on the particles has an effect on the collisions. So if we increase the concentration of solute, what happens is there's a greater number of particles in a given volume, and then that leads to an increase in the frequency of collisions, and so the overall rate of reaction increases. And so an answer to a simple exam question that asks you to explain how rate of reaction increases with the increased concentration, these are the components you're looking for. You want to always follow this cause, particles, collision, overall effect. Obviously, decrease would be the opposite here. You have a decreased number of particles in a given volume, decrease in frequency of collisions, rate of reaction increases. So we're going to use this same model to explain each of these scenarios here. So increasing the pressure of gas, this is very similar to concentration of solute in solution and follows the same conceptual ideas as we've talked about here. An analogy to understand these is the idea that if we had people in a room as our reactants, so each person is a different reactant. A successful collision would be if they collided and caused damage to each other, for example, maybe invoked a nosebleed. An unsuccessful collision would just be that they bump into each other but with no actual harm caused. So it's gone slightly dark approach. However, in terms of basically linking these abstract ideas to something more concrete, if we were to increase the concentration of solute in a solution, that's like taking the same area where these people are walking around blindfolded, bumping into each other, and then just adding more people in there because you've increased the number of particles in a given volume. Therefore, as they're walking around blindfolded, they're more likely to bump into each other. The frequency of collisions increases. But what's important, okay, is that when they collide, it doesn't necessarily mean they're going to collide with any more energy than the activation energy. So the activation energy remains unchanged. Increase the pressure of the gas. Very similar idea, but obviously we've got the same number of people in our room, but we've just shrank the room, okay? We've increased the pressure. We're putting the particles in a smaller volume by decreasing the size of the room. So that could be a hall compared to a normal classroom. Hall is obviously a lot larger. That's low pressure. High pressure is the classroom. And then people, when they're moving around, are particles. They're more likely to bump into each other, and therefore their rate of reaction increases. So we've looked at basically aqueous solutions. We've looked at gases. Next, we're going to look at the idea of a solid. Now, surface area only applies to solids. And if we take this cube, which has a particularly low surface area to volume ratio, but we were to increase the surface area of a solid, then more reactant particles are exposed at the surface. And you can see here, if we split this cube up into 8 smaller cubes, then it has a higher surface area to volume ratio. So as particles outside of our solid, and this could be like a solid catalyst, if there are particles outside that need to collide with it, there's more surface area that's exposed versus this low surface area to volume ratio. And so we have an increase in the frequency of collisions, and so the rate of reaction increases. Now, if we increase the temperature, that's like telling our particles, our people in our analogy, to run around faster. Therefore, they're more likely to bump into each other than moving slowly. And also, when they do collide, they've got enough kinetic energy to overcome the minimum energy for a successful reaction, the activation energy. It's really important to notice that we have an increase in successful collisions, those with an energy greater than the EA. This, in all the other ones, has only been the frequency of collisions. It has no actual effect on the amount of those collisions which are more or less successful. Only temperature has this effect. And finally, if we add a catalyst, then the rate of reaction increases because a catalyst is a substance that speeds up a reaction without itself getting used up, and it speeds up this reaction by providing a alternative pathway of lower energy. Now, to use another analogy, we could imagine that this is a bit like high jump, and our particles' successful reaction is them overcoming the bar. If you add a catalyst, that's the same as being able to lower the bar in this high jump competition, so more people can jump over it, and therefore the rate of reaction increases. And just like temperature, there will be an increase, therefore, in the number of successful collisions, those with an energy greater than the EA, as this has been lowered. Now we're going to turn our attention to Boltzmann distribution curves. If you were to take 100 students that sat a test, you'd get a distribution of their marks in that exam. And so if we were to plot this, we would have number of students, or the frequency, on the y-axis, and their marks in the exam on the x-axis. So imagine, on average, most students got 60% in the exam. So if we make this 100, and we've got 50 here, then the peak of our frequency is going to be roughly here. Everything else is then distributed around that. Not every student got 60%, that was just the average. And so we come up with basically a bell curve that may look something like this. And so some students got over 60, some got below 60, and we've got this curve here. And we can show a similar distribution called a Boltzmann distribution, which actually shows the kinetic energy of the particles, A and B are reactants, against the number of particles with that energy. Now, a successful collision would be if A and B hit with enough energy to form C and D. And we know that this minimum amount of energy required is known as our activation energy, or EA. So on our x-axis of our graph, we're going to have to designate a certain kinetic energy to be our activation energy. So let's just mark this point here. So any particles that have more energy than this EA, this activation energy, will undergo a successful collision. So any particle in this area of our distribution will change into C and D. Now, some key characteristics about a Boltzmann distribution is that your curve for this distribution must always start at 0, 0. Now, the reason is there are no particles that have no energy. It's also theoretically possible that our particles will have no upper limit on their kinetic energy, and so our other end of the distribution will not meet the x-axis. So we're going to form a distribution curve that links these 2 points together. Noting that it never touches the x-axis on the right hand side because there's no upper limit, but will always start at 0, 0 here. Now you can see the mean average, our kinetic, the most probable energy for our particles is here. And so you could read that off the graph down here. And going back to our activation energy, if we extend this line, you can clearly see that any particle found under the area of the curve here of this distribution, they will undergo successful collisions. So imagine this is a distribution curve at room temperature and pressure, so standard conditions, and this is the activation energy. Now I'd like you to think about what would happen if we increase the temperature to this distribution curve. Pause the video here, sketch down what you think might happen, and then you can check the answer. Okay, so if your curve looks like this, then you've got the right answer. Now, as temperature increases, then you can notice the shift of the most probable particle energy has moved upwards because the kinetic energy on the x-axis, we obviously shifted most of our particles to have more kinetic energy. Now, with this shift, okay, comes the fact that we also need to keep the area under the curve, this red curve, exactly the same as the area under the green curve. And we've roughly tried to approximate this because it shifts to the right, but also shifts downwards. Noticing also that previously in this green shaded area, these were the particles or the area of particles with enough energy to undergo a successful collision. With this new curve, we have more particles that have the activation energy, so undergoing a successful collision. What I want you to do now is try to sketch the curve that would occur if you had a lower temperature. So pause the video, have a go, and see if you can take the ideas that we just talked about and apply it to this new scenario. Okay, now if your curve looks like this, then you've taken those ideas and applied them correctly. One thing to note is the curve has shifted to the right. This is because our most probable area, the highest point of our curve, equates to a lower kinetic energy. The area under the curve to keep roughly the same needs to therefore decrease here. And you'll notice that on this side, our activation energy, and this links to collision very nicely, there is less particles in this area under the curve that are beyond the activation energy. So next we're going to look at the effect of concentration of a solution, and we're going to imagine that this curve here is a high concentration. So what would happen if we lowered the concentration, say by half? Think about what is going to happen. Will it affect the frequency, the highest point, the most probable point of kinetic energy? Will it affect the number of particles in this region here? And how will the overall curve look? Pause the video, have a think, sketch it down, and I'll give you a couple of seconds before we reveal the answer. So, if your curve looks like this, then you've got the right answer. You'll notice the shape of the curve, forgive my drawing, is exactly the same. But we've reduced the area under the curve by roughly half. And also the number of particles in this region of the distribution, i.e. those with more energy than the activation energy, is roughly half as well. But the proportion is exactly the same in terms of this area here for the green area as a percentage of the overall area of the curve is exactly the same as this area here as a percentage of the overall curve of this lower concentration. And also, just to reiterate, it should start at 0, 0 on this side of the axes. And also, you'll notice this doesn't touch the x-axis on this side because we have no upper limit on how much energy a particle can possess. The next scenario we're going to look at is the effect of adding a catalyst on the distribution of molecules. So again, imagine this is our curve, our distribution with no catalyst. So I want you to pause the video here and have a go at drawing the distribution if you were to add a catalyst to this system. Okay, if you drew this distribution curve, then you've got the correct answer. So you'll notice the curve is exactly the same. However, one thing that you should have added is a line to designate the activation energy, and we're going to call this EA cat for catalyzed, and EA uncat we can relabel the original as uncatalyzed. And so you'll notice that there are now more particles in the area of the distribution curve that have the minimum energy required for a successful collision versus the original uncatalyzed. Okay, now it's time to try and put some of this all into practice. So here we have a typical Boltzmann distribution curve. What I'd like you to do is to take this curve, firstly to label the x and y axes, and then draw some different curves to show different conditions changing. So pause the video now and attempt these 4 different tasks. So these are the labels that you should have used for point 1. A decrease in temperature should look like this. Remembering key features is that it always starts at 0, 0. It's going to be taller, so it shifts both to the left and up for a lower temperature. And the number of particles with the activation energy is lower. A distribution curve for a lower concentration should look like this. Remembering that the shape of the curve is pretty much the same as the original one that you're comparing to. And finally, a distribution curve to show the introduction of a catalyst will only lower the activation energy, so you'll get a new line for activation energy for a catalyst. But the curve would remain exactly the same as the red one originally. Okay, so that concludes our lesson on collision theory and Boltzmann distribution, where we started by looking at qualitative explanations for how collision theory can explain increases in rate of reaction to do with different conditions in the reaction. And then we looked at how this manifests itself in a Boltzmann distribution graph ticking off these different things of activation energy, looking at temperature changes, and then also the proportion of molecules. If you found this video of use, please ensure you like it and subscribe to the channel for more videos relating to A-level chemistry.